Okay, it's a great pleasure and honor to introduce John Martinis here. It's actually always a great pleasure to listen to his talks, but today it's a particular pleasure for obvious reasons, I would say. And actually, it's also a great occasion because John Clark has joined us too to listen to John Martinis' talk. So it's 2 out of 3 here. It's a reunion of the two of them. You know, I should say that you know that as a theorist, I particularly appreciate John's style of working on experiments because it's, you know, his thinking it's always big and bold, both in terms of ideas, but also in terms of going big, in terms of scaling. So, you know, I remember.
I'll talk about.
Oh,
that.
you'll talk about that.
Yeah,
okay. So
that's my talk.
Okay, great. So, well, then without much ado, I'll let you start.
Yeah. Okay. Thank you. Yeah. Thank you for the kind invitation. This happened before the events last week, and I always like coming here and talking. And I'm really glad John's here. John, I really appreciate that you woke up, was it 2 in the morning, and answered all these questions. And my wife, and I think Michelle's wife, purposely shielded us from this. So thank you for your service.
It's a great pleasure.
So yeah, let me just start with these wonderful experiments we did here in Berkeley in the 1980s. I wanted to start with, you know, what was the basic question what we were doing? Do macroscopic variables obey quantum mechanics? And I'm very proud that in one of the papers, that was the first sentence of our paper, really drawing people in. Now, what was funny, the story, I'll tell you a story. The story is I was in France visiting Michelle, who was trying to recruit me to go to postdoc, which I did. So we went out to dinner, and we wanted to talk about the introduction. Okay, and what I remember from that conversation is that what you do not want to do is say, recently there has been a lot of interest in blah, 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 okay? And I don't know if you've ever written a paper like that. Don't do it. I mean, are you doing science to please your fellow scientists and do something because it's popular? I don't think anyone goes into physics to do something popular. Okay, we go into physics because we want to answer questions. And I really like this because it focused in what we were trying to do there. So why do we want to do that? Well, we all know about the Schrödinger cat, and you know, there's various ways to think about this, but Professor Tony Leggett had a really interesting idea, is that the Schrödinger's cat collapses to a classical state, one of the two, because quantum mechanics is not allowed on a macroscopic object, fundamentally. And you know, there's just some new physics of that. Now, in my mind, there's actually some physics that's been worked out in the quantum information era, kind of describing what's going on there. Some people are still mystified by it, that's okay. But the basic question is, well, can you see quantum mechanics on a macro level? Now, let's talk about what that means. One of the interesting things is quantum mechanics is observable at the macroscopic level. That's been known for years and years. You take, for example, a crystal here, and the atoms are put together with the binding between the atoms in a certain way, and it turns out that they can bound in a very regular order way, so that the macroscopic view of the crystal tells you something about how the atoms are actually stacking up. And of course, you can do X-ray diffraction to kind of figure that out in more detail. Same thing happens with superconductors. It condenses in the superconducting state, and you can get some order parameter that gets carried in a macroscopic way in terms of the same way. There's this order parameter, and then you can see that. What we're doing here is showing that the whole macroscopic object shows quantum mechanics. Now, you can think of this simply, let's say, as a carbon buckyball, lots of atoms. And this is actually done by the Xylem group. You can put it through a proper diffraction grating or double slit and see the interference from that. And of course, what we're doing with the superconductors is this is a condensed state with millions or billions of electrons in it. You know, seeing that the currents and voltages obey quantum mechanics, that is constructed in this way. So this is the idea. I do want to say, what you want when you get your PhD thesis, it's really common for people to kind of want to repeat that later on because it was such a great experience. So I was really happy in the past 5 years with Google to look for macroscopic quantum computation, okay, where you're computing on a gigantic Hilbert space of 2 to the 53, about 10 to the 16 individual states, and that is properly getting computed by the quantum computer. And now it's even bigger than that. So that's been great to go from a very, you know, much more simple experiment to something very complicated with quantum computation. So just to talk about the experiment a little bit, here's the picture on the left. And you know, I was very proud of that at the time. There's a lot of engineering in that. You know, of course, we're beyond that. The chip is down here, and if you look closely, there's a little T here of the wires, and it's the currents and voltages here, those variables that are obeying quantum mechanics. And then this is very carefully engineered to go up into a transmission line with a wire inside here with copper powder on the inside, which acts as a damp transition line. And that gives you filtering that you're going to need to make sure you thermalize to the proper temperature. Here's the thermometer. Here's a microwave injection point. Then it comes up here, and the wires go down to additional microwave and radio frequency filters. You have to get rid of all the low temperature noise. And then in the end, you know, that goes up to room temperature. And then here is a SMA attenuator, kind of hard to see. You could buy that back then, that was no problem. But we couldn't buy good coax, so we had to make our coax ourselves from copper nickel capillary and figure out how to do that. Now in the experiment, what we have is basically we're looking at a weak link in a superconductor where for small currents you see the superconductivity, and then you go above a critical current parameter, and then it switches and looks like, you know, the normal state of that system. And then as you get close to the critical current, you basically can describe that with a Boltzmann statistics Arrhenius law on what the rate is that you see out of it. So you can express the actual rate you measure in terms of a T escape, e to the minus delta U over KT escape. You can change the temperature, and given the definition and the behavior of Boltzmann law, you see T equals T escape at high temperatures, and then at some point when you get down to low temperatures, it flattens off here, okay? So, you know, that would be an indication of quantum mechanical behavior, but how do you know there's not noise or something going on in your system? So we did a bunch of check experiments, including putting magnetic field on this junction and reducing its critical current so that the frequency of oscillation was lower and it's more classical. And in that case, you know, you get close to the T equals T escape at low temperatures. And then, of course, we were able to measure the actual parameters, the frequencies of the qubits and the like, so we can get a zero adjustable parameter prediction of the macroscopic quantum tunneling, which is very good with that. So that's the first part of the experiment. And again, key ideas, check experiments. You know, lots of work came in to do this. And hardware, we have to understand that it's a microwave experiment and that you have to do really good filtering or else room temperature noise will swamp you. Now, if you want to prove something quantum behavior, if you go back to the early physics of quantum mechanics, a key thing that people observed was quantized energy levels. And if you think about the electromagnetic behavior, and let's say a Bremsstrahlung radiation, it's going to radiate in a continuous spectrum, but what you see in atoms is the discrete energy levels of the light, let's say, coming out of an atom. And that's because there are standing waves due to the wave function of the electrons, and only certain frequencies want to oscillate in the system because of that. And that's a really distinct prediction of quantum mechanics. So what we did in this experiment is we measure the enhancement of the escape rate with microwave power, without microwave power, as we change the critical current. Okay, so as the critical current gets higher to its bias current gets close to critical current, the frequency goes down. The qubit is flatter, and then the potential barrier is smaller. And as the current is less, bigger. So, and as you work out the quantum energy levels here, you see at a lower bias current, frequencies higher, and you can see a 0, 1, 2 to 3 transition that helps you escape. And then as you go higher and higher at a fixed frequency, you start going into resonance with the 1 to 2 and 0 to 1 transition. And you can see that barely in this plot. This came out of a dot matrix printer. That's how primitive plotting was back then. So I'm sorry, took the dot matrix printer and gave it to the graphics artist to make the figure. But you can see it. There's a big peak here, smaller peak. They get wider, as you expect, because of the matrix elements and the like. And it agrees fairly well with what you expect, with an experimental uncertainty. So, this is the basic experiments, and, set up the idea that you can do that. And with this, with energy levels, that, you can make qubits out of it. And that's what people did over the years, is thinking about that. So, many, many experiments around the world for many years. People investigated this, really thought a lot about the physics. And, culmination for me was when I was at Google in 2019, we published the quantum supremacy experiment. Here's all the leads going into it. Instead of, one wire coming out of here, maybe 2 wires for the microwaves, you have all these control circuits for 53 qubits, complex fabrication in there that's unfortunately hidden, but, there's a lot of work there. So that was a real pleasure to see in, 34 years, going from the basic experiment to something very sophisticated, showing you can do complex calculations. Of course, next we have to make it powerful. Make it be as powerful, we have to make it useful. Now I want to talk a little bit what I'm trying to do right now, okay, with my startup company, Qolab. And, if you look from here to here, this is much more sophisticated fabrication, which no surprise. But I think if we continue with this kind of fabrication and this idea, we're kind of in a box canyon right now. We can do a little bit better, but I don't know how we're going to scale up to millions of qubits. Okay, that's going to be hard. And what I want to talk about is that we're going to make a fabrication leap, 2019, let's just say 5 years in the future, that is as big as the leap from here to here. Okay, and that's what our company is about. That's what we're going to try to do. And I think if we want to be successful, that's what we're going to have to do. Okay, that's absolutely necessary. So my story next is, okay, what's behind this? Now, it's easy for me to say that's what we want to do, but we actually have a detailed plan. And if you were to look at this archive paper, we'll update it soon and get a better version of this. But we wrote a paper saying how are you going to scale from hundreds to millions of qubits. What's interesting is we have a lot of people advance this, a lot of companies, but besides, startups and maybe, maybe some university, whatever, we're bringing in industry players like Hewlett-Packard Enterprise, who make supercomputers, hopefully NVIDIA, they know how to do powerful, hopefully decoding. Synopsys, they build design software, and most importantly, Applied Materials, who knows how to build very state-of-the-art complex vacuum systems and processes in order to do that. And it's kind of really, we think this is the way to do it. Take advantage of what's going on in the semiconductor industry. Use that technology. It has to be used right, but we think we know how to do that. So I'll talk a little bit how we're going to do this. First of all, I want to talk about why we're doing this. There's a very personal reason for me. So, here's quantum supremacy. That's great. If you look at the history of what's going on, let's say for superconducting qubits, things that I was involved in, at UC Santa Barbara, we had 9 qubits, early error correction, moved to Google, got the quantum supremacy experiment here. That was really great. Showed that a quantum computer is powerful. Quantum mechanics really works on the macro scale. And at the time, the industry expectation was, give ourselves a year, and we'll be able to get up to 1 million qubits. And that's kind of what people talked about, what Google talked about. So how did we do? Okay. And here, when I talk about the number of qubits, this is actually a proxy for the improvement that's what's going on. Because in all these experiments, qubits got better, algorithms got more sophisticated, and this is just some way to talk about it. But in half the way to a decade, factor of 2. Okay, maybe a little bit more now. Okay, so that worries me. This is why I'm in Qolab. Okay, this really worries me. And if you extrapolate, I'll tell you why. If you extrapolate this and think about when we're going to get to 1 million qubits, I will certainly be dead by then. No question about it. And I'm going to say that most of the people here will at least be retired. Maybe worse. Okay, this is taking too long. Okay. So how do we increase this pace? And increase the pace, in my view, is a lot of things we have to do. But I think we have to do the hardest thing, which is to learn how to fabricate these devices better. Okay, so that's what we're doing, is trying to figure out, figure out what's doing that. So I'll give you a basic outline of that, okay. So the first, again, most important thing is advanced semiconductor fabrication. Okay, so number 1, superconducting qubits are made with something called liftoff, which you put photoresist down, you pattern it, and then you use that as a stencil to make the junctions. Okay, this is a technology of the 1950s and 1960s. And I would like for anyone to tell me, is a professional fabrication company right now using liftoff, okay, to do this kind of thing in a serious way? I'm sure there's some processes that might work, like a back-end last thing or something. But that is not a serious thing. How are you? And if you look at what people are doing, and a little bit of that, people are having problems yielding 100, 200 qubit devices. That's hard. And if you look at like the IBM roadmap, which is published, it's based on tiling 120 qubit devices. And there's a reason they stopped at 120. Okay, and I'm going to say it's mostly this, but I'm sure there's other things too. And it's just hard. So what you have to do is make it in the modern way, which is deposition and etch. So this is an example. We worked with Academia Sinica, ITRI in Taiwan. We used SiO2 with a window in it, evaporating aluminum, and then etched away the SiO2 scaffold so we can make devices that don't have liftoff. We only got a couple devices to work. They work okay in the tens of microseconds, 30 microseconds, but we definitely have to do better, and we're working on that with applied materials. Okay, the second thing you want is clean interfaces. Okay, and what we can do, and this is an example of aluminum film on silicon. You notice how flat that aluminum film is. You don't see that very often, okay? This is an atomically clean transition. Now, this can be done by cleaning your silicon wafer and then walking quickly or running to the deposition chamber and putting the aluminum on it. But the thing is, Applied Materials knows how to do that completely in situ, in a vacuum, do that very, very reliably. This is good. And then the third thing we're going to talk about in a few slides is wafer scale integration. Okay, and that's how all the modern chips are done. So we'll talk about that. And then, of course, there's a ton of other things that I'm not going to tell you about because, you know, they're work in progress. But it's actually hard to do it this way. There's many, many things you have to figure out. So it's kind of a risky business, but I think there's no other way. Okay, just talking a little bit about system engineering. You have to do a lot of things to get this system to work right. We need to lower our qubit errors, make them better qubits, we're trying to do. You have to be able to scale them up, which we're going to show you how. You need to have good connectivity. More is better. Surface code for nearest neighbors works good. But you know, we saw today that with the atoms, where you can move them around and move them in parallel, you can increase your connectivity and improve things a lot. So, you know, this isn't the only way to do it. I'm going to say speed. You really need speed to run utility scale algorithms. And superconducting qubits are great. It's maybe a little bit faster than 50 nanoseconds. Atoms are great. There are a lot of things. They're intrinsically a little bit slower. It's about 100 microseconds to move things around. That's about 2,000. Maybe with serial execution, it's even worse. Now, of course, as we learned this morning, neutral atoms can be slower, but you can have more connectivity to effectively speed it up. So there's a really interesting engineering trade-off between the two. But this is really fast. This is good. And that's why I think, you know, superconducting qubits have some kind of advantage. So this is all the technical stuff. But I really want to point out that the thing that really matters, and especially if you're trying to build a company, is cost. Okay, no one talks about that. But you have to build your quantum computer in a cost-effective manner. So when you look at the current technology of superconducting qubits, this one program we did, they estimated it to be in the tens of billions of dollars. Okay, people are not going to want to fund or buy that. Well, maybe Google's making enough money and they can do it, but that's really not what you want to do. And we feel that by doing the integration that we're talking about, you can bring this down to, you know, let's say $100 million. It's still expensive, but that's what supercomputers cost now. And big data centers are in the billions of dollars, where you know that you're going to get return on investment. So we're really, in this integration, we're trying to do that. Okay, so I want to spend a few minutes about what it's like being in a startup company. This whole sphere talking about here is kind of the Qolab detailed marketing pitch to the VCs. And they don't like this at all. We have not, this is the bad pitch. Okay, I think it's true scientifically, and you know, I see other people doing it. That is the bad pitch, okay? And what they want to hear is that you have some magic physics, and you look at this and you pick out the one or two things that are really good, okay? And you talk about the magic physics, and then they think, oh, you know, if we just fix these couple things, which are going to fix, then we can build a quantum computer and we can make a lot of money. That's what they want to do. That's fine. Okay. But of course, if you build anything complicated, it's the worst things that matter. That's what limits you. But no one ever wants to talk about the worst things. Okay? It's just not what you do to the VCs. So that's the real dilemma, at least we found, is we're trying to be honest about what we're doing and why. And it's kind of difficult. We've been successful for Series A. We'll get a Series B. But that's hard. Now, I do want to talk about the third way to pitch this. And the third way was only available to Qolab since last week. And the third way is to have a celebrity endorsement. Okay. And everything's changed now. I'll let you know. Yeah, things are looking really interesting. I'll let you know in the future. But I have to work on my marketing pitch. But now I can go over this. I want to be honest, but you can be honest now. Okay, so this is what's really cool. Thank you. I really appreciate that. Okay, I'm just going to say here that, in fact, what's really hard here is, besides all that, you have to meet benchmarks. And I think, Sergio, if you look at these benchmarks for Martin, they're more or less what you did. And we came up with them independently, and maybe they'll be a little bit different. But, the nice thing about super companies, we know what we need to build. And that's really good. And, we're all working towards that. So, there's a lot of things you have to get right. And there's much more on this than here. I'm sure you guys certainly know about that. So that's good. You need to do that. Okay, you need to have the picture. Okay, so we have multiple dilution refrigerators connecting together with various QEC orchestrator and accelerators. Lots of GPUs to do the computation. Custom ASICs to drive it. Okay, all of this is in our paper. But if you need to pitch something, you need to have the picture so that people know what you're building. Okay, so that's, and then, here it is for the qubit fabrication at the my materials. This is a modern 300 millimeter tool. These are 300 millimeter wafers. You have one common vacuum system with many process modules out here. And what Applied Materials has done is put the process modules together that we need on one of their existing machines. We can run our process, and because it's kind of an existing machine and they kind of already know how to do things, it's relatively inexpensive to do that. This is, $100 million machine. Okay, we can't afford that. Okay, and then by working with them, we get to work in their. This is their old thing, old $4 or $5 million clean room with all these machines here. We have a lot of capabilities there. They're building the new clean room that you will be able to use. So this is really the way to do it. Okay, so let's talk now about, what is this thing going to look like? Okay, how are we going to build this? So this gives you a schematic view of what we're going to build this. And the key idea is to use wafer scale integration. This is an AI company, classical computing, that makes a chip out of a full 300 millimeter wafer. Now, when you build that, you can't yield 100% yield, so there are clever ways to route the data around so that they can get this to work. I think that's a $1 million product for one wafer. But, very, very interesting. And yeah, this is what we want to do. But we don't have to yield, I don't know, trillions of transistors. We just need to yield, it turns out, 20,000 qubits, okay? So the basic idea is we have a qubit wafer that's going to be about this big by this big, millimeter spacing, and that comes out to be 20,000 qubits. And, that's the special magic that you have to do for qubits. And then we bump on that to another wafer, a wiring wafer. That's a 300 millimeter wafer that brings the wires from 20 millikelvin to 3 Kelvin, okay, on a single wafer. And if you space the wires by a little bit less than a micron, you can get 100,000 wires, in transmission line form to do that. So that's, there's a lot of wires, it's escape wire, but you just brute force. Because of superconductivity, they can be tiny little wires, and you can have a lot of them. Now, I think John is nodding his head. I'm a little bit worried here, because he knows, and a lot of people here knows, that the thermal conductivity of silicon is like that of copper. How in the hell is this ever going to work? Well, what we're going to do is basically thin out the wafer, so that there's a small, let's say, cross-section between here and here, and then you can lower the thermal conductivity so that you can think doing that. Then there's going to be a lot of thermal engineering and heat sinks and whatever here, but when you go through the numbers, you can do that. And this is, to us, this is the key idea, is to do integrated circuit wiring. and you can bring wires out, and you can thermally isolate it. Now, you wonder if this is going to work. Applied Materials made a test wafer that's sitting in our lab right now, and we're making a little jig, and we're going to measure the thermal conductivity. We think we know what the physics is, but we're going to test that out right away. And, I think it should work. I understand the physics, but, we'll be able to do that. And I think we can kind of take the thermal conductivity of copper and make it like brass. Okay, so John's shaking his head. Okay, good. I'm glad John approves. And you can, you'd like it to be much better than brass, but that's enough that you can imagine doing it. So there's a lot of engineering there. Then you bump on that to another wafer, which we'll call the cryoelectronics wafer, where we put chiplets of squid amplifiers and CMOS control circuits or whatever we need there. And you can make little classical circuits and test them and bump on them on there. This is classical electronics here. And because it's not at 20 millikelvin, but it's at 3 Kelvin, you have a lot of cooling power available for you to do that properly. So we think this is kind of the right mix here. And it's kind of interesting that your qubit wafer, since you connected all these electronics and turned the electronics, you're not doing anything here but cooling it down. I mean, the wiring's all in this module. So you make a module, about this big, and then you bring copper alloy flex that I'm working on, and you connect it perpendicularly to the wafer and bring it up to higher temperature. I think the right way to do this is have all your CMOS control at 300 Kelvin. It's high power, waveform control, water cooled, and then do some smaller digital I/O to bring it out. Okay? And then, that's 20,000 qubits. We have to make modules. We just tile them together, let's say in a line. There's other ways to tile it. And then you do capacitive coupling between the qubits along the tile. People have already shown that you can do that. But, of course, you have to do a lot of mechanical and qubit engineering to get that to work. And so this is, 120,000 qubits, maybe about 1.1 meter. That'll fit into one big refrigerator, what people are building right now. Okay? Now, for those of you who know about this field, the big problem is reading out the qubits in the fact that you use big circulators, they're about that big, maybe smaller, two-phase amplifiers, all these big components, okay, that makes it really hard to do. What we're doing is using something that Robert McDermott invented, of a qubit connected to a microwave photon kind of single photomultiplier that can convert the measured qubit states to a tunneled or not tunneled state of a qubit system. So we map a qubit into a resonator, either 0 or 10 photons. Then we basically have a phase qubit, which then you don't have to drive it very hard, and it either switches or not switches. If it's 0, it has one frequency, 10 photons another, and then you just multiplex that out just using the standard frequency division multiplexing that we do. And then you can use a squid amplifier at 3 Kelvin, which is about a factor of 2 greater than the quantum limit. So you need a good amplifier, but it's really low power. This is microwatts, very low power. So you can do that, and then you go up to room temperature. So I'm not going into this in detail, but Robert did this experiment. There's about 1% errors. It worked right away, got it to work nicely. I'm sure it can be improved. And we can integrate that. These are all much smaller than the 1 millimeter squared qubit cells. So you should be able to do that and solve and crack the readout problem. And this is low power. It has everything you need. And then if I talked about here, we coupled with capacitor couplers to connect them together. And then when we make this big array, you have these connected dilution refrigerators. When you cool down, this shrinks by a few millimeters. and then you're going to have some kind of flexible microwave connection from one to the other to scale it up. You know, all the qubit systems are talking about things like that. I would say the advantage here is the microwave photon interface. We did the basic experiment here in 2019 at UCSB. We showed how to do that with, you know, the fidelity of around, I think it's around 99% that we were able to do that with. So it exists. We have to make it better, but we don't have to invent anything new. The technology is there. So we'll get working on that eventually. 221. Oh, I'm doing we have to stop at 2:30. Just for, you know, making these junctions is very critical. I'll just explain that in more detail. Make our aluminum, we put SiO2, and then we etch the SiO2. Making vias in SiO2, that's the one thing that the semiconductor industry really knows how to do well. Okay, and the kind of the resolution they can get with this that we're beginning to see in the lab is just really, you know, mind-boggling. Nothing you could ever think about in an academic process, because they know how to do that. You then plasma clean that, oxidize it, put metal on top, and then etch it. And then as the final stage, you use vapor HF to etch away the SiO2. And then it's freestanding. So you can see the pictures here. So we've done this. Yeah, what is it? 57 microseconds. It's okay. It's not as reliable as we want. We'll get this to work better. Okay. So with that, I'm going to just kind of start summarizing here. I told you that the most important metric is the cost to mass produce. And, you know, as this is a physics conference, you generally don't talk about that at all. That's something we're really thinking a lot about if we're going to make this thing. And what I'm going to say is most of these things, yeah, we feel okay about. Fabricated in qubit and wafer carrier, this is mass produced. You don't need to build a $4 billion clean room. We can do it in the Applied Materials R&D clean room, and they're committed to do that. Bump bonding and mounting, we have to develop that. This has been done, but doing over a 300 millimeter scale, people know how to do this in the semiconductor industry. CMOS control, we'd like to do that, use cryo-CMOS. Room temperature CMOS, no problem. Cryo-CMOS, it's okay. This is not large area, not too expensive. Flex wiring, PCB manufacturer. I'm working with a contract manufacturer to figure it out. Dilution refrigerator, custom, expensive. If we have to mass produce it, I'm sure the price will come down. That's something we really have to work on. And it's a big part of the cost, but not, you know, not like 90 or 95%. It's something. Assembly and testing, yeah, that's a big thing. We're going to make modular qubit modules, 20 qubits. And one of the things people don't talk about is what is your reliability? And like I said now, it's hard to do more than a few hundred qubits with the reliability. And we think if we use a proper semiconductor fab, you know, they're making, you know, billions or trillions of transistors. We should make, you'd be able to make 20,000 0.1 micron, you know, window junctions. That, you know, that looks very reasonable. The critical area is very small. So, you know, we have to do that. We think that's good. Room temperature locked electronics for Nicole, mostly off the shelf. So, you know, we look at this, everything looks good. We'll have to work on the dilution refrigerator. What I like about dilution refrigerators, and manufacturers are trying to automate that more. And I think you can bring the cost down because of that. Okay, I'm going to just say that, you know, when I look at the hardware efforts in superconducting qubits, they're great. They're making good progress. But there's challenges that I believe are unresolved or maybe overlooked that I think we're in a box canyon. We can be proving, but it's going to be really hard to break out of that. And I think we can leverage the semiconductor industry, totally accelerate that. We're doing that with a consortium. And yeah, the plan is scale to 1 or 5 million qubits with wafer scale integration. and do that in a modest amount of time. There was a government program that talked about 2033. That's hard, but I think with the right funding and using the semiconductor manufacturers, they'll know how to save us, really. So with that, thank you very much for your attention.
Thanks, John. Are there any questions?
Thanks for the very nice talk. Is it well understood how to handle the wafers with the backside trenches? Because that would, I'd imagine, mechanically weaken the wafer
yeah,
quite a
so that's something if I were to tell you, I would have to kill you. That's the saying.
The secret sauce. I see. Okay.
There's a way to do this that is very clever and very nice, and it's based on things that they're doing production in the semiconductor industry. So I proposed something, and then the people at Applied Materials said, well, if you do it this way. And we went back and forth over a weekend with about 30 emails, and we finally, came across. And that's what we're testing right now. But we have to make sure, we have to measure the conductivity, heat load, and we have to measure against our models. And that's what we're going to do in the next few months.
Oh, very cool.
Sorry, we'll let you know. But what I like about this is if we can really get this to work, people who are building like astronomy detectors, photon detectors, or other thing, you might be able to use that technology to make a bunch of really interesting things. Because the wiring between 20, 30 millikelvin and 3 Kelvin is a real pain in the neck. And if we can simplify that and get that engineering right, so I like the idea of doing that. And the magic is when you have a superconductor, there's no loss and there's no thermal conductivity. So you can make it really small, and we're just trying to take advantage of that.
You're talking about this enormous wire density to get all the information out. And what I wonder is there a problem with crosstalk?
Yeah.
Do you do anything special to mitigate the crosstalk?
Crosstalk is a big problem. And you have to worry about both the DC currents and the RF currents. And we've been doing a lot of research to understand that. And we have some really simple models, physics models on how that works that I don't think anyone knows about yet. We'll eventually talk about that. That it's really important to understand. We're also working with Synopsys. Okay, they make like HFSS, other tools. And we're working with them to figure out how to scale up the tools to measure big chips. And trying to understand that. We're at a pretty simple level, but we would like to do that. But we really want to develop physics models, because if you just do a simulation of these things, it's hard to mesh it tight enough to do it right. And there's other ways to do it, we think. People are talking about that. But we're trying to talk to the experts. But we have good physics models. We have good design philosophy models, and this is absolutely essential. Yet you don't want to tell the venture capital people that you're working on this. This is the problem. I mean, you have to tell them something, but you don't want to emphasize how important it is. But we think it's absolutely essential. And people are doing brute force simulations and doing things. That's really great. But when we look at that, you can get the direct parameters out of it, but getting crosstalk, that's really hard. So, But for example, you take the wiring wafer, that's sandwiched in between two ground planes, and that should have very low crosstalk. So I'm not worried about the classical control, okay? And getting the classical control routed to all the things. That's okay. It's kind of the quantum crosstalk. or the control crosstalk, with the nearest neighbor. That's the problem. Yeah, that's good. Thank you.
One last question.
Someone over here.
Cool. Yeah. Thanks for the presentation. Really interesting stuff. Oh, great. You pulled up the right slide. So I wanted to ask you a little bit about the logical qubit bus. Do you have any design paradigms that you want to push through with that? In the literature over the last 20 years, that seems to have fallen by the wayside, and it's sort of interesting.
With your mask, I
Sure.
have very bad hearing.
Yeah, sure. So could you elaborate on, what you intend?
Someone else can repeat your question. That might be good too. Umesh, do you understand?
You ask again.
I'm sorry, I have horrible hearing.
Sure. Just about the logic bus.
Sorry, he's asking about the logic bus.
About
About the logic bus, the
the
logical
logic
qubit.
parts. On the cryoelectronics wafer?
The logical qubit bus.
The logical
Oh,
qubits.
the logical qubits. At 20,000 qubits, that's maybe 20 logical qubits, roughly. And then, you can move it around and the like. So those are physical qubits, 20 logical qubits. You tile it up to bigger. Okay? Is that okay? Well, you have the surface code arrays, so you can do whatever you want with that resource, is the idea. Now, let me tell you something. If you make your tiling of 120 qubits, you look at the IBM roadmap, Rigetti is making 9-qubit tiling. Okay. You would expect that between the tiles, you're going to get a little bit of degradation of your qubits. And the last thing I want to do is put that degradation in the middle of a logical qubit. So we're trying to make this big enough so that you can have many logical qubits and, do things properly. Because across the tiles, it's going to be small delay or not quite as good or something. However, because you're only connecting it on a tile, and it's just one connection out of the 4, then you're a little bit less sensitive to the error there. And it can be a little bit worse. But we're really trying to make it big enough so that you can just put in logical qubits there. Now, I would say that we're using, 2D nearest neighbors, surface code like Google's doing. We understand that's good. IBM wants to have 6-qubit connections at long distance. That's really hard to do. They can figure out how to do it. That's great. But, I'm trying to build something that we kind of know how to do. And maybe later we'll figure out how to do something more complicated. That's great.
Thanks a lot, John. That's really exciting.
Okay. Thank you.